So this is supposed to be a tutorial. Now, just to push the guild, I was planning and counting on giving a normal research talk, but then the organizers, specifically Cesare, who is not here, he escaped my rage, contacted me and said that they will lose funding and they're not going to have a fourth tutorial. So can I please give it the same lecture that I gave in the magnetism school in Vienna, which was oriented mostly for student and graduate student. So you, in this audience, I don't think that hardly anybody who would learn anything new, but you know, without that, otherwise they probably wouldn't get money to pay for all of us there. So they just have, I have to suffer through the lecture, and you have to suffer through listening. So, okay, yeah, don't pay attention to this. This is wrong. So, as a sort of tribute to Daniel Chomsky, this is a quote from a poem by Kipling, which he and I both like very much. And this is a poem about how to compose tribal leis, which is like tribal hymns or songs. And I wiped my mouth and said, "It is well that they are dead, for I know my work is right and theirs was wrong." I think that's a sentiment that is very familiar to many of us. But my totem saw the shame. From his ridgepole shrine he came, and he told me in a vision of the night, there are 69 ways of constructing tribal leis, and every single one of them is right. So even though many again, not in this audience, but very often I was approached by people asking me, so we understand what superexchange means in terms of Hubbard model, but you guys, you do DFT, not even, sometimes not even DFT plus U, and you claim that you can calculate magnetic interaction, but you don't have Hubbard interaction there. How come? So basically, the interesting thing about that in one or another form, essentially all magnetic interactions that come out from many-body perturbation theory are also built in density functional theory. Although there are some important nuances, and sometimes it's useful to keep that in mind and think about that. But overall, generally speaking, the physics is surprisingly nearly always there. So in this, because it's so-called tutorial, first I will tell you a few words about spin density functional theory, which you all know anyway, and then lay out things in a more systematic way. I will speak about two major things in which DFT can possibly fail, or what is missing from DFT, and then it just as an example of how various things work. These are like 5 arguably most common exchange interactions that we encounter in textbooks. I will just tell you in what specific way do they appear in DFT or LDA or whatever you want to call it. So for the purpose of this talk, I will compare that density functional Hamiltonian with a Hubbard Hamiltonian. Right, so you immediately see that there's many commonalities. Like, for instance, this is the Hubbard energy. This is which is Coulomb, not Hubbard, sorry, Hartree energy. Essentially, Coulomb interaction of density with density, and this is exactly this term. Note, by the way, that this is of course much more accurate than this. So again, very often, and it's very unfortunate. I think it's very detrimental for our science that many people believe that plus is always plus. So if it's LDA plus U, it's by definition better than LDA. If it's LDA plus U plus DMFT, it's by definition better than LDA plus U. That's often being the case. It's not the case always, because these are 3 different approximations. And sometimes when you you may be throwing a trivial baby with the water by trying to account for something which is not really important for this problem. So anyway, so this is it. So this way, as it's written, is essentially spin density interaction, which is again accounted for here. This is a term which is missing, and it's an important term. It's a and it's sort of inherently not akin anything that we can have in density functional theory because it's orbital dependent. And there's this, as you know, this very important, as I just mentioned, LDA account better of special variations. And Hubbard model does many different things, but arguably the most basic one is that it avoids self-interactions, self-Coulomb interaction and self-exchange, which in methodology like Hartree-Fock cancel out automatically. They do not, by the way, they, depending on how you implement it, they may or may not cancel entirely in all these LDA plus schemes, but definitely they are accounted on the basic level. So obviously self-interaction is an important thing for localized system where physical electrons are well localized, and the self-interaction is an important chunk of your total energy. As electrons become more and more itinerant, like in good metals, this is become eventually 1 part of 10 to 23 and become unimportant. So to be more specific, when we speak about local correlations, not necessarily just self-interaction, this exact LDA plus your DMFT Hamiltonian depends on the double counting. And that is for that very reason. So that would be completely idiotic to throw away these terms because spatial variations are extremely important and absolutely needs to be taken into account. Which means that if you add them again, that you have to subtract something which is closely reminiscent of this term. And then people opinion diverge. There are different ways of doing this double counting. There are, the general concept is that you keep LDA. I will speak LDA, although GGA can also be and so on. You understand what I mean. Then you add something additional, and then you want to subtract not LDA, but you want to subtract this additional Hamiltonian, treat it in a way similar to LDA, reduced. And then, unfortunately, there's more than one way to do this reduction. So these two things are clear. They are just obviously accounted for in LDA, so we can throw them away. What to do about the last term? So here you can say that, well, let's say that this is that this function is a function of total spin. That would be in LDA spirit. And then there are two schemes. There are probably more than two, but these two are the most common, and this one becoming more or less standard nowadays. So in one, you do this DFTization by replacing density number by average over all orbitals, and then your function becomes like this. You can check that, and then this delta V that you have to subtract, basically the delta V essentially appears to be the difference between the orbital occupations for each orbital and the average orbital. So this scheme sort of like a perturbation over the state where all orbitals, like all d orbitals, are more or less equally occupied and small fluctuations. That's why it's called around mean field. It probably maybe even better to say just around mean, around average. Now in some sense, a conceptual disadvantage of this scheme is that this scheme already implies in the beginning that correlations are weak and deviation from DFT are small, while the regime where it's actually important to add Hubbard U is the opposite limit where electrons are well localized. So in this case, you make another assumption. You decide that your occupation numbers are either 0 or 1, full localization. In that case, this function x that I was talking about becomes this, and then delta V is essentially, well, that should be a subscript, that actual occupation minus 1/2. That essentially pushes down all occupied bands, pushes up unoccupied bands. Well, I'm sure that in this audience, everybody knows that these things are maybe dramatically different, but not everybody who starts doing these calculations realize that. And the best one way to see how different they are is to try to. We all know that LDA plus U is generally more magnetic than LDA. So the question is, can we cast that, say, like in effective enhancement of the Stoner factor? Yes, we can, because by just taking derivative with respect to full magnetization, right? And verify the mass that for fully localized limit, you add, essentially you add to your Stoner factor this effectively, some approximation, this addition, which is effective u minus j divided by 4 for d orbital, that would be 5. So given that u is usually considerably larger than j, it's often a very strong enhancement of magnetism. In fact, in this approximation, which is much less used now, its first approximation is 0. There's definitely nothing proportional to u minus j here. So the second important ingredient missing in LDA is, besides local correlations, are some fluctuations. Definitely some fluctuations, particularly fast fluctuations, which are already present in our reference system in the uniform electron gas, are included on some level. But there, of course, are fluctuations beyond that. We also know from just general quantum theory that if you have a mean field theory of magnetic transition or magnetic state, and you include quantum fluctuations, so those fluctuations, or thermal fluctuations for that matter, but even quantum fluctuation at 0 temperature, then they reduce this local spin by some number depending on the lattice, and could be between 0.1 and 0.3. And itinerant fluctuations, which are like something which is close to itinerant ferromagnet, for instance, very typical, then can do all many things, and some of them are included in the reference system, and that essentially gives rise to this von Barth-Hedin and other famous schemes. But if you look at the real materials, say, well, this is BCC iron, and this is average density of states, including all electrons or just valence electrons, and then you look at the phase diagram of uniform electron gas, you can see that this density, at this density of states relevant on solids, for solids, in classical electron gas, really nothing interesting happens. It doesn't even polarizes. So in some sense, it becomes increasingly less good reference system, and sometimes it becomes important and needs to be corrected. And there's not an unusual or extremely rare situation. And believe me, this is just a very small small selection of all of the various materials where these itinerant fluctuations appear to be very important. For instance, there are a number of materials where LDA severely overestimates this magnetization. These are what people sometimes called weak ferromagnet, but that not to be confused with scanted antiferromagnetism, which is another weak ferromagnets. So these materials have magnetic moment experimentally maybe of 0.1, 0.2 Bohr magnetons of that order. And DFT, LDA, and even more so GGA overestimate this magnetic moment sometimes by as much as factor of 5. Then there are materials which LDA predicts ferromagnetism and experimentally they are not at all. So this is a reduction is so severe that it's that they become non-magnetic. And then there are even larger class where LDA considerably overestimates spin susceptibility. In fact, SR2RU04 that you heard about quite a bit already, it's interesting in a way that in GGA, actually ferromagnetism is lower in energy than paramagnetism. In LDA, it's not the case, but still. But by the way, so far here I was speaking only about ferromagnetic fluctuations. SR2RU04 has a very, very strong magnetic instability in any density functional calculations at a finite wave vector. So it's essentially a spin density wave, and experimentally it is not. And it's probably all spin fluctuations. And of course, iron-based superconductors, the parent compounds, is another strong example. So this is a very simple explanation of what's going on. And that goes back to Moria. And in fact, this theory was laid out in his famous book, decades ago. So essentially, suppose that this is a mean field total energy as a function of magnetic moment. We know that everybody can do that by doing these fixed spin moment calculations. And you can see that iron and aluminum has a gain of magnetic energy of about 0.2 electron volts per formula at magnetic moment of about 0.6 Bohr magnetons. So it looks like a very decent ferromagnet. Now, what Maria said, well, let's assume that there is that quantum fluctuations essentially make what this red dot, which represents this instantaneous state, fluctuate like this. You can see that by construction, this curve is asymmetric. I mean, it always is asymmetric. So that means that average over time, and we can suppose that these fluctuations are Gaussian fluctuations, and then he did all this algebra and got some numbers. So we see that this ground state will be gradually shifting towards lower magnetic moment. In fact, you can try to implement, in some poor man way, to implement Maria fluctuation theory in DFT. And if you do that, you can estimate the amplitude of these fluctuations as 0.47, which is about that large. And if you include that in Maria sense, you get something which is very, very flat, super paramagnetic, but not ferromagnetic. Similar situation with zirconia zinc 2, which is in the calculation is a very, very strong ferromagnet. But if you include these fluctuations, it becomes a very weak ferromagnet with magnetic moment close to experimental. So,
May I ask, are these thermal fluctuations?
No, quantum fluctuations.
Quantum fluctuations.
Quantum fluctuations, yeah. I mean, obviously, Maria's theory includes thermal fluctuation and quantum fluctuation. He does a lot about temperature dependence on various things and transport matrices. There's a lot of that in this book. But
this numbers on the horizontal line.
in Bohr magnetons.
Sorry?
Bohr magnetons.
Bohr moment.
Yeah, it says magnetic moment in Bohr magnetons.
And this one is just the numbers of moments.
I'm sorry, what?
This magnetic moment.
So this is magnetic moment.
Yeah, this is magnetic moment in Bohr magneton. This is energy in electron volts. So electron volts are not this. Yeah. Okay. So I'm switching gears, going to the next subject, and then the next long section will be, again, I will go one by one through typical magnetic interaction, and just to show you how why density function calculations actually can predict or can describe sometimes correctly, sometimes less correctly, all these typical magnetic interactions which we learn about in context of many-body perturbation theory. So the simplest thing to start with is this antiferromagnetic direct exchange. So now you know the DFT is in some sense one electron theory. So, and then also this fourth theorem that was mentioned before one of those days that helps us put rigorous basis under counting one electron energies as a energy difference between two different states. So let's count one electron energy. So suppose first that I have a ferromagnetic arrangement, and that means that my the generating level is split into by plus minus t, roughly, when t is some scale of electron hopping, includes coordination number, whatnot. And the same happens in for spin minority. Again, it's one electron description, so there is spin majority band, spin minority band. It's not a perturbation or some intermediate state. This is just one electron band theory. Now, the energy difference between these two states is, in pure DFT, is magnetic moment times Stoner factor. In LDA plus U, it would add to that Hubbard U, but it's basically a cost of flipping electron spin or Kohn-Sham particle spin and moving it to the higher level. Now, so this is ferromagnetism. Now, given that this in the lowest order in T, this moves up and this moves down, the average energy of these two occupied states does not change. On the other hand, if we consider antiferromagnetic state, then of course, again, in density functional theory, no spin orbit, this state hybridizes with occupied state up here. So this one is pushed down, and correspondingly this state is pushed up. So as a result, I have this electron state moving down by t squared over u, and this electron is moving down by t squared over u. So I have energy gain per bond of 2t squared over u. It's a short range with u, or in pure DFT it would be mi, but basically it's a scale of kinetic energy squared divided by the scale of energy cost of flipping an electron. So it is there. And by the way, sometimes people who, again, I'm sure not anybody in this audience, but sometimes people who start doing calculations get surprised that you include more correlations and your calculated antiferromagnetic exchange is going down. Of course, it's going down because, and it's in LDA plus U, it's very often you can see that it scales in the first approximation reasonably well as 1 over U for this very reason. So now, superexchange. Superexchange is essentially a similar thing, except that you introduce one intermediate state here, and then your nearest neighbor tight bonding model looks like this. So you have D state, P state, well below, and hopping. T now is hopping between oxygen or whatever ligand and metal ion. So when you integrate out oxygen state, then you get uniform shift of both D state, we don't care, and then there is an effective hopping between the two metals. So that works. For instance, that would be X, something like XY orbitals, and Y, PY orbital of oxygen, or you can have the same in the EG channel. That's effectively the reason for crystal field splitting, and you get effective hopping of 2t squared u, where t is now itself quadratic in one electron hopping. What about ferromagnetic 90-degree superexchange that Daniel was talking about before? So here you have an interesting situation. So let's say we are speaking about T to G orbitals. So let's say these orbitals. So these orbitals can hybridize with this and only these oxygen orbitals, while at the same time this state can hybridize with this and only this oxygen orbital. So these two states are orthogonal to each other. So they cannot. So there's no way for electron to hop from here to here to here. So when we write this this tight binding Hamiltonian, instead of what I had in the previous slide, you would have 4 by 4, and then these two oxygen states will not talk to each other. So there will be no antiferromagnetic exchange here at all. However, ferromagnetic exchange will appear, and it will appear seemingly in a very different way than it does in many-body perturbation theory, but actually it's the same, and the functional form is the same. It's very much the same. The way how it comes is if I start hybridizing oxygen and metal, then that means that there is small admixture of oxygen state in what we call in DFT metal bands and other way around, and that admixture is proportional to t squared over delta, where delta is this charge transfer energy. So now there is, again, as Daniel was also explaining, there is Hundruls coupling on oxygen, which is not small. So basically in DFT there is small spin polarizations induced on oxygen. So this spin polarization, the standard formula, there is Stoner energy or Hundruls energy is I m squared, where m is magnetic moment induced on oxygen. So it's roughly I t to the 4 delta 4. And the I here is a Stoner factor on oxygen. So remember that if this bond would have been 180 degree, we just derived it in the previous slide, then the antiferromagnetic superexchange would be 2T4 divided by delta square U, while our interaction is IT4 divided by delta 4. That means that the ratio between these two interactions is IU divided by delta square. This is a very normally it's a very small number, and this interaction is much smaller, and it can only appear in 90 degree or very close to 90 degree when the antiferromagnetic interaction disappears. That's actually an important part, because if you go back to the previous slide, then you can realize maybe that in DFT theory there is something like self-interaction of spins also. So the fact that this one single orbital here is spin polarized in DFT as opposed to many-body theory actually gives rise to the same contribution of ferromagnetic by nature and proportional to Stoner factor on oxygen. And it slightly reduces the effective energy difference in DFT, but usually it's not that big a problem for that simple reason that it's a small contribution. But that's an interesting thing to keep in mind, that this is sort of like a fake ferromagnetic coupling in DFT. Now, okay.
Why do you call it super exchange? Why not direct exchange?
I don't call. I mean, people just say these words. It's an accepted terminology, but
the way you interpret it, so it's like you have some tails on the neighboring sides, and you have some exchange interaction.
Yeah. No, absolutely. I mean, I will come to what again. There is some terminology in the field, and people use word super exchange every time when there is another ion involved in between. And in fact, I had fights as a referee with some respectable people writing papers who were not just using this terminology, but essentially interpreted that as a something conceptually different from direct exchange, which I agree with you is not the right approach. But but I will also speak about the direct exchange in most rigorous sense, when there is nothing in between and the tails overlap in empty space. So yeah, but again, it's unfortunately in our field, terminology is not always the most enlightening. Sometimes the same, like let's say people say metamagnetism, and people mean at least two absolutely different, unrelated concepts under this terminology. And if you're going on into nematics or topology, then it's a whole zoo is just called an elephant because elephant is big and attractive.
But anyway, in your talk, you're talking super exchange whenever you have another atom in between.
Yeah,
and you call
yeah.
it,
And it doesn't mean that I endorse this terminology, but I'm using it.
Okay, so that's it. You define it.
Yeah. Okay, now let's speak about something else which is less common known, but again, that's something that Daniel mentioned in his talk, is multi-orbital superexchange. So this 90 degrees is not the only way to gain ferromagnetic interaction, and it's another interesting example. So suppose that you have crystal field splitting, and you have T2G and EG orbitals, and let's say this is, for instance, would be the case in something like chromium triiodine. So this is 3 electrons, 3 orbital fields, 3 orbital fields. If I make this ferromagnetic, right, then I can now let me remember if I can do it right. So there is. Oh, I'm sorry, because I need to remind myself what I was doing here. So basically, if you in DFT, that means that that if I have antiferromagnetic configuration, that means that that the bands are shifted by exchange field, which is in DFT is like 3I, right? So that means that if I want to that my hopping from N now the important thing is that if as you see in this case there is no hop, we just saw in the previous slide, there's no hopping between two similar kind orbitals. So if this is, for instance, let's call it XZ, so XZ cannot hop to XZ, but XZ can hop to this orbital, and this orbital can hop to a T2G orbital here. So there is, in this approximation, there is only effective hopping between T2G and EG orbitals. So I cannot hop from here to here, but I can only hop from here to here. From here to here. Now you can see that this hopping is larger than this hopping. So the energy difference here is DCF, and here it's DCF plus 3I. So In both cases, this, like in standard superexchange, this state will go down and will gain kinetic energy. But this gain will be smaller in the antiferromagnetic arrangement because you divide by a larger denominator. If you now expand that in powers of I over crystal field, which is not exactly a very small number, but in some sense the standard perturbation theory also makes the same assumption, and then you get effective ferromagnetic interaction of that order, which you may remember is about the same, basically it's the same functional form, and I think maybe it's exactly the same coefficient that what Daniel was deriving from any-body perturbation theory. The advantage of doing it this way, well, obvious advantage of doing that Daniel way is that you have direct understanding of the processes that lead to this interaction, and you can gain a lot of physical insight. On the other hand, on numerical level, again, there's something I have some sort of personal beef with. Very often, people who are doing calculations, they extract parameters, then put these parameters in some simplified Haber-Hund model, and think that this is better than actually calculate energy difference. No, it's not better. There might be something like this fake ferromagnetic interactions corrected, but there are many, many other different processes here that are not taken into account in a simple model. And DFT, total energy difference, or Lichtenstein perturbation theory, for that matter, account for all these interactions simultaneously and on the same footing. So I think, generally speaking, it's a better way to calculate things. Now, what about ferromagnetic kinetic exchange? And I will argue that this is, again, speaking of terminology, this is, again, the same roles called by any other name. And this is with the same physical processes in different regime got called double XC, and another context people use this moniker RKKY, but physics is always the same. So what is this physics? Again, now we are looking at the same starting model. So this is spin majority level, spin minority level. This is the separation which we discussed already. But and now I'm getting this a bit more. Now I'm not treating that as two individual particles or two individual sites, but as a continuous chain or plane or whatever, and that so that interaction generates a continuous band, which is symbolically depicted here. And the width of this band is, roughly speaking, coordination numbers times one electron hopping. And obviously, we get on this level of reasoning, we get the same band shifted by exchange splitting. Yes.
Are you talking about insulators?
Hold your horses. We'll get to that. So now, let's say that we are now doing the same thing with antiferromagnetic arrangement. Then the splitting between these two bands becomes larger, and this dispersion becomes smaller. Now, if this is an insulator, then it's all irrelevant. Because who cares how this weight is distributed as long as the center of gravity has not displaced. But now suppose we have a metal. I see you are relieved. Now suppose we have a metal. If we have a metal, then of course we have to count in this one electron energy scheme only the occupied part. So the center of gravity of this occupied part will now be displaced from a chemical potential, but something of the order of minus ZT. Well, as coefficients, they will be coefficients, of course, due to the structural density, but that's the same thing. And the same will happen here. So now we see that now we have gained a linear energy, and here we gain only quadratic energy. So this is, of course, much better. And that means that if you have a metal, and in fact, the closer you are to middle of the band, to have occupied metal, the stronger this thing is. If you get closer to the top, then you will go into what people call double exchange regime, and there will still be some ferromagnetic interaction, but it will be functionally somewhat different. But this is a decent and strong interaction. That's the reason why most ferromagnets, of course not all, but most ferromagnets are actually good metals. So Now, ferromagnetic energy gain is maximal for half filling. This approach gave rise to several very useful tools, which unfortunately few people know. Now I may come to the point which even somebody in this audience may not know, possibly. And this is extended Stoner theory, was invented by Ole Anderson. And that's related to this Anderson force theorem, which also was sounded off earlier in this conference. And it says the difference of one electron energy calculated with the same charge density is equal in the lowest order to the difference of cell-consistent total energy. This is extremely important tool because it essentially tells you that instead of doing two self-consistent calculations, you can do calculations with the same fixed charge density and only count one electron energies. And that not only gives you a possibility to do calculation maybe faster, but it also gives you a possibility to analyze things in a very transparent and simple level. So basically, it works like this. So suppose you have something, and then there is this whatever charge distribution, and I want to calculate energy difference of cutting this piece of metal of solid apart and shifting it, right? So obviously, we know that these wave functions will change, everything will change, and in principle, we should calculate total energy here and total energy there. But what happens is that you can do calculations like this and only count one electron energy, and the energy difference will be the same in the lowest order of the perturbation introduced, in this case, like in this gap size. So there is, how much time do I have?
22.
22. Okay, well, maybe I can then.
Perturbation theory in what?
Hmm?
You mentioned just perturbation theory in what? In previous slide.
Oh, in something. Basically, whatever is the measure of the perturbation is in physical sense that is introduced in the system. In this case, this is you did this cut and then you shifted them, right? So this gap that you opened will be your perturbation parameter. In some other case, it might be something else. But whatever change you introduce in the system.
So you are go to show us how these.
Yeah, so right now, so this is, I mean, you may not want to follow, but this is, in principle, it's easy to follow. This talk will be online. So this is the way how Anderson derived it. So he started with the standard Heisenberg functional, right, written in this way. The main important thing is that it's assumed that before you made this change in the system, your calculation was fully self-consistent. So now what you do, you calculate your kinetic energy, which is this, right? And you calculate your, so this is your kinetic energy. And then for this purpose, you have to subtract this, and you have to subtract that. And this is the Kohn-Sham potential, which is just variation of one. This includes Hartree energy and exchange correlation energy. So this is this thing here. So therefore, we can write total energy in this form, right? So this is just rearranging terms here and explicitly writing, expanding kinetic energy. Now, suppose that the external potential changes by some delta. And this delta, self-consistently, when you have recalculated your everything and re-self-consistent, generates new density, change in density of delta R, and change in one electron, an effective one electron potential of delta VEE, right? Then, to the second order, we can just take variation of this expression. So then you get this term. We get this gives us this term and this term because this is two variables here. Then you can see that these two things cancel out exactly because it's by definition of VEE. Right? These two things cancel out exactly by definition of kinetic energy. And what is left is one term, and this is I, delta ext I. I are the starting wave function. So again, this is this famous quantum mechanical theorem that basically tells you that this is nothing but sum of the change of one electron energies. Yes?
Yeah, am I right that the first theorem is only valid when the perturbation is small, whatever perturbation you have?
Well, I mean, generally, any perturbation theory is valid only when perturbation is small.
So then, in some cases, it will not work when the perturbation is large.
Yes, that is correct.
Yeah, I will ask this. What are those cases when we should be considering that force theorem can fail?
I mean, I personally think that force theorem, the most useful part of force theorem is conceptual rather than computational. So to me, force theorem is an extremely useful tool to analyze the results of fully self-constituent calculations. But there are cases, and I'm not going specific, when this is actually happening. Like for instance, many people, and there's always a risk that you may be inadvertently going beyond the limits or your accuracy is not enough. But for instance, very often people calculate magnetic anisotropies by using force theorem, and it works reasonably well. Also, and for instance, this theorem is explicitly used in deriving this Liechtenstein perturbation theory for exchange interaction, which is widely used. And even though...
Actually, it's very disputable because there was a paper by Patrick Bruno, and he argued that there would be some additional contributions in order to enforce this magnetic force theory.
Maybe, maybe,
So
yeah.
yes, strictly speaking, it doesn't work in the Liechtenstein's formula, and there are some corrections.
Yeah, I mean, I personally,
But it's very close to.
I'm very skeptical. So I always try to verify that by doing some direct calculate energy difference as well. But yeah, but anyway, I'll give you on the next slide. I'll give you an example when I think it works very well and it's extremely helpful in analyzing your results. And unfortunately, relatively few people do that. So this is what Ole called extended Stoner. Maybe he didn't call it extended. Maybe somebody else called it. But anyway, he invented this. So the story is like this. So suppose we just want to understand your fixed spin moment calculations. Fixed moment calculation is a very popular tool and it helps you understand things like metamagnetism and whatnot. So he did this way. So suppose you have you introduce uniform magnetization, which you can consider to be a perturbation in this sense of force theorem. That basically means that you take some number of spin minority electrons and move them into spin majority band. By doing that, you gain some Stoner energy or Hundre energy because it's quadratic in magnetization, but you lose some kinetic energy, right? So exchange splitting introduced in this way is nothing but m divided by density of states per spin. You have energy gain, which is really this, and you have energy loss, which is this. And by comparing these two things, you get Stoner criterion. In DFT, in Stoner original paper, it was Hubbard U. In DFT, it is Stoner I, which is just second derivative of exchange correlation energy with respect to total magnetization, and it should be larger than 1. Now, what Ole asks, so why don't we apply now, move a little bit more of spin minority electrons and apply force theorem again? So now, remember, it's not applied to the original state, it's applied to this state now. Then you have to integrate this energy difference, and you arrive at this expression where this n bar is density of states average over all this splitting. So basically, this number of electrons divided by this splitting. So the way how if you want to, it's easy to calculate, you have density of states. Basically, you keep shifting your density of states until you reach the prescribed number of electrons. Then you calculate how much you shifted them. That gives you this, your n bar. So this is an example for, I forgot what, for this material. It's very unstable because you have the peak of density of states. And if you start to split this peak, you need really very small splitting to gain particular magnetic moment. And for that reason, obviously for m prime going to 0, n bar is just density of states at the Fermi level, which it is very large. Now, then it rapidly goes down because you're looking into this deep minima in the density of states. It goes down, and now it falls below below this line, which I will explain what this line is, and then it goes like this. Now, what is this line? This line is if you actually now take this expression and take the derivative, first and second derivative in magnetic moment, you can see that the minimum of this expression, which means a metastable, not necessarily the most stable, but a stable magnetic state, so some sort of a minimum in total and in fixed spin moment calculations, when this density of states, this n bar, is equal to 1 over I. It's easy arithmetic. You can, well, not arithmetic if you take derivative, but doesn't matter. So in this case, so this is another story. If I don't take into account Hund-Roos coupling on oxygen, then my 1 over I, ruthenium I, would be this number here. And that means that I would have, yeah, and by the way, for that zero to be minimum energy, not maximum, the second derivative, so it should be, the derivative of density of state should be negative. So this is a stable magnetic state, ferromagnetic state. That means that without magnetic interaction of oxygen, there would be a magnetic ground state in DFT calculations at about 0.4 Bohr magneton.
Chemical formula have a strange.
Huh? What?
Chemical formula have a strange. Oxygen.
Yeah.
What is? Huh?
06 probably.
Oh, 6, of course. Yeah, 06. Yeah. Sorry. 06. You know, I gave this talk several times. Never noticed it. Yeah, 06, of course. Yeah. This is. Yeah, this is standard double perovskite. But anyway, I mean, forget about the formula. Doesn't matter what formula. It's a general discussion. So anyway, but this is a perovskite structure, and they are oxygen connecting ruthenium metal ions, and in ferromagnetic state, oxygen is polarized very weakly. I think the calculation is about 0.1 Bohr magneton, something of that order. But that still gives you some additional contribution to net Stoner factor, and if you take 1 over total Stoner factor, it becomes that it's very important. It becomes now this, and now this is about 2.7 Bohr magnetons. And if you actually do self-consistent calculations, that's what you get here. At this moment, it's we enter another thing, which is Stoner theory for compounds. Again, that is relatively trivial, but for people who starting to do density functional calculations, sometimes this part is missed. So this is the essential definition of Stoner factor and density functional theory for the entire compound, right? Magnetic moment, for instance, in this case, can be calculate magnetic moment on ruthenium and 3 magnetic moments on oxygen, which is a small addition to the total thing. Now, magnetic moment, if you have rigid shift, magnetic moment is proportional to partial density of states. That means the total energy can be written in this way, which is atomic Stoner factor for ruthenium scaled with partial density of state of ruthenium squared plus 3 same contribution for oxygen. So that leads us to this formula that average Stoner factor for a compound, in this case it's for this purpose neglecting everything else, is ruthenium 03, it's scaled like this. Now on DFT gives you for ruthenium gives you 0.7 electron volts, pretty sizable, and for oxygen it's 1.6. This is a bit bigger than spectroscopists usually take, but that's again, this is just numerics, not that important. Now that means that if you take only ruthenium, you get a Stoner factor of 0.41. So that is and if you do and that's as I was showing before, if you do only this, then you would get a magnetic state, but very weak magnetic state. When you add oxygen to that, then your Stoner factor is raised. I forgot, I didn't write it down. I think it's raised to something like 0.52 or something, but that's already enough to shift your to create completely different new null magnetic state. So by the way, as Igor already mentioned before his question, this is nothing but a multi-atom analog of the classic Heisenberg ferromagnetic exchange.
Are you sure that this oxygen moment is not tail of ruthenium moment? You will get the same result if you just dab part of the same moment in one place, and you will get rising.
No. The reason is that actually that creating magnetic moment in empty space definitely gains magnetic energy, but creating spin polarization on incompletely fooled p orbitals of oxygen gains you more magnetic energy.
But
so
you check that it's pure.
Yeah, so it's the same physics, but it's stronger. if there would be ferromagnetic interaction, it would have the same physical origin, but it would be weaker. And in some sense, it probably can be traced down to the fact that also Daniel mentioned that paradoxically, the Stoner factor or Hundruls coupling for p orbitals on oxygen is actually way stronger than the Hundruls coupling for d orbitals on a metal. So now let's go back to what this expert in the audience have already pushed me several times to discuss, and that's ferromagnetic Heisenberg exchange. So that's the way how it does is, yes, you have this two-wave function and they just overlap. When they overlap, then there is this total, and again, there's various ways you can write that's exact quantum mechanical theory for that, but my goal is to show how this interaction appears in density functional theory. So it appears the following way. So this is my total magnetic moment for two cases, for ferromagnetic and antiferromagnetic case. So in this case, this spin densities add, in this case is subtract, so I can calculate the total Stoner energy. I deliberately don't call it Hund energy, this is like Stoner energy in density functional theory in two cases, right? So I can subtract them, and what I get Stoner factor times overlap of the wave functions, of squared wave functions. So the larger the Stoner factor, the larger this effect is. However, if it's not, in most cases, when this direct overlap occurs without any intermediary, it appears to be negligibly weak. And let me show that. So suppose you have just pure d orbitals like this. So there's no, if there's something sitting here which hybridizes, it's all different. But there's nothing. This is just exponentially decaying tail. And then I can see that can calculate ferromagnetic and antiferromagnetic exchange. So ferromagnetic is this number, and antiferromagnetic would be just direct exchange, which we discussed in the very beginning. And I can estimate T by taking kinetic energy operator and doing this very rough estimate, and I can find that it will be proportional to this number. So if I take now the ratio of these two exchanges, it's about I squared RD4, it's about 10 to minus 3. So if you just have a typical distances of transition metals, this direct exchange is pretty small compared to all previous issues. So and in some sense that density functional calculations include that by definition. So there's not a big problem anyway, whatever small it is. Now you can see papers that say, well, we see strong direct ferromagnetic exchange in our calculations. So how these things could be? The thing is that it's misleading one-year function. It's now a very, very popular exercise, and we saw this many many times here people do calculations by creating this maximally localized one-year function, this 1-year 90, whatever it's called, so on. And then they completely forget that the origin of this one-year function is more complex than just atomic orbitals. So they're not atomic orbitals. They're something else. And if you look at this typical thing, you can see how large is the weight of this one-year orbital on the neighboring ligand. So one-year function overlap can be as huge as Trump's inauguration crowd, but in reality, it is not like in this example copper D, but it's oxygen P on the same side that overlaps. So now I guess I will just stop whenever my time is over. But next point on our agenda is a double exchange. So this is how hopping. One electron hopping proceeds. You have, say in this case, you have a hole, it hops, right? That's all. Now, this is how hopping proceeds for antiferromagnetic arrangement, and it calls for, say, for this case, we have it's like manganese oxide, for instance. It's 5I or U, so you have a much smaller dispersion. We already went through that. Now, you have energy gain of the order of T, and it's long-ranged. So this is more or less the whole thing is the only difference between what I discussed is in this case I have one hole, and in the previous I was alluding to sort of like half field. But you can see the physics is more or less the same. It's just numerics that might be somewhat different. Moreover, it might be even more general than that, and it also occurs quite many times, even though people don't identify it. So let's assume that some electrons are forming local moments and some are itinerant. In reality, this might be, and usually are, the same electrons. They just pile up their moment near the nuclei. So then the Hamiltonian would look like this. For small JH, we can integrate out itinerant electrons that you can find in these excellent textbooks, the best of them, which is, of course, Daniel Chomsky textbook. Everybody who doesn't have it should go immediately to the bookstore and buy one.
Why not?
Yeah. So then when you do that, then this is essentially, when you have integrated out, that you get what is called RKKY interaction, and you can clearly see the double exchange is nothing but RKKY interaction in a small occupation regime when these oscillations are very long range. That's it. So you see this is a formula, and then it's...
Okay.
Yeah. I think something along that line is written in one of your paper as well.
No, my understanding is they can be derived from the same model, but in different regime.
Well, that
Double
was,
exchange is very large splitting and very narrow bands. And RKKY is opposite.
yes and no. I think they are derived in different regime, but the difference is not the size of splitting, but rather, well, you mentioned two things. The second thing I think is important. It's the filling. Yes. That double exchange is the same model in small filling regime. RKKY is the same model with a good metal in large filling regime. But double exchange can actually be derived at the particular limit of RKKY. Yeah. Well, let's see. This is well. Let's see here. This is in double exchange. You have very small Fermi level, so this is more. In a good metal, you have large Kf, and then you have strong oscillations. So this is my spin, my localized spin here. And then I want to put an electron here. If I put an electron here for small Kf, that will be my nearest neighbor. Will definitely be ferromagnetic. This is my ferromagnetic interaction. In RKKY, it can fall into on the hill or in the valley, so it can be. It will be changing sign. So this is all. This is, yeah, I had some cartoon to that effect, but somehow it didn't work right. Oh, no, it does work, just too slow. I don't have time for that. So you can. So this is a standard double exchange model again from Daniel's textbook. So you can solve it, and the solution is spin canting, or in real life, it's more often spin spirals than spin canting, but in principle could be both. And you get that. Another interesting misconception about double exchange is a double exchange, even though in the original paper it was envisioned as a itinerant and localized electron that belong to the same atom and are coupled by Hund rules. In fact, that's not really a prerequisite to double exchange model in a way. And this is a very good example here. So this material, which is barium, manganese 2, arsenic 2, intercalated with barium. And barium can be, it's an insulator, good semiconductor with good gap. And you can hole dope it, and then magnetic moment of manganese obviously is a good antiferromagnet, start canting. Why do they do that? I mean, the top of the doping goes entirely into arsenic bands, nearly purely arsenic P. And magnetic moments are on manganese. You may think that it's not a case of double exchange, but it is. And the reason why it is, yeah, and also, by the way, manganese moments, if you, another example is that if you start with zinc, which is also divalent, and it's non-magnetic insulator, and start adding manganese, nothing happens. But if you start adding manganese and potassium, also hole doping, that manganese impurities start ordering ferromagnetically with very large critical temperature, typical double exchange. So let me skip a few things, but go to these important things. So this is looks like a little bit busy slide, but in fact it's easy to understand. What I'm speaking about here is that you have localized level of one metal. of one species, and this is this spin down band. So in this case, it's just one line. And then there is itinerant band. In this case, it's arsenic band, which goes through. Now, there is hybridization between manganese and arsenic, which can be described like this. So what it leads to is that it means that this is, if you have spin up here, then spin up subband of this itinerant band will be pushed up, and spin down will be pushed down. So there will be very small, but not negligible, net polarization opposite to polarization of manganese. So that's, you can see this interaction is described by exactly the same Hamiltonian as double exchange, except that the sign of the coupling is opposite. Before they were trying to line itinerant and local electron were trying to line up parallel. Now they want to try anti-parallel. Now, if you remember on the yes, oh, that was better. If you well, let me skip that all. Now you remember that in double exchange formalism, Hundrell's coupling was always entered quadratically. So it doesn't matter whether it's positive or negative. It's exactly the same Hamiltonian, exactly the same physics. So anyway, so this interaction, by the way, has a name which Daniel taught me. It's called Schrieffer-Wolff interaction. And you can write explicit expression for this interaction, but let me skip that. So,
Why is it counted?
huh?
Why is it become counted?
It's double because it's double exchange.
No, it's okay, but
Well, double exchange is
whatever
ferromagnetic.
exchange,
Hmm?
what reason
Double
for
exchange is
counting?
ferromagnetic.
Between superexchange and double exchange.
Oh yeah. No, there are two different compounds I was speaking about. This is manganese, pure manganese compound, where you introduce holes. Then what happens is that you have really strong antiferromagnetic standard superexchange, and on top of that you get double exchange. It's exactly like the Gen. It's exactly like the Gen. Yeah, absolutely. Yeah.
Whatever you call exchange, with isotropic exchange, you can't be counted.
What?
So there is a competition of.
It's a it's
Any competition between isotropic
Well,
exchange can
okay.
give you
Take your beef with the Gen, not with me.
Maybe spiral.
without relativistic interaction, you can't be counted.
No.
Maybe spiral.
Actually, yeah, that's very good advice. Go and buy Daniel's book. It's very well explained there. Okay, now.
Actually, there were claims it's not cutting, it's space separation.
Could be
phase separation, yeah. But could be in this case experimentally scanting. But we had long arguments with experimentally about it. But we don't have time for that. Anyway.
Something new or finished?
No, I'm finishing. I just wanted to show off my education in classical Shakespeare. That's all. So that is now okay. No, this is something new. So I will skip that and. Let me just finish this thing. There are two different ways to gain knowledge from calculations, particularly from first principle calculations. If the calculations agree with experiment, the next step is to go inside and dissect them step by step, which is something that Volker Heine was advocating from long ago. And then we can see we can check what mechanism is operating as operative, what role is the structure played, how does chemistry affect the result, and so on and so forth. And if it fails, it's also might be useful because you can gain knowledge from that as well. Like for instance, for high TC cuprate, so the first indication of strong correlations was that LDA failed to reproduce magnetic moment. In high TC pnictides, the first indication of a strong role of long-range spin fluctuation was that LDA failed to reproduce a paramagnetic state. And for instance, in the high TC pnictides, the first indication of nematicity was failure of LDA plus U to reproduce orthotropic distortions without magnetism. So anyway, that's my last slide. Thank you.
Question.
May I ask about Maria formula and quantum fluctuations? So, you have one of your first slides. Could you just maybe?
Oh, that would be probably long flipping.
So
Keep talking, I will.
If we have thermal fluctuation, then I can easily know the yeah. So if this would be the thermal fluctuation, then I can easily calculate, the fluctuation.
The amplitude.
Yeah, the amplitude from the
Yeah.
temperature, right? But how did you calculate this number, say 47?
Okay.
From
Well,
quantum fluctuation?
following-
How do you know the amplitude?
following your master's voice, we took, well, actually, it was not really that. But if I if I had read Morier book carefully at that time, I would found the recipe there. Because basically, you take fluctuation dissipation theorem, then you make a reasonable approximation or relate expansion of spin susceptibility in terms of Q and omega using your calculated density functional band structure, and it can be related to particular parameters of the Fermi surfaces, such as like second derivative of plasma frequency. What? Unfortunately, I was not careful, so basically I rederived all these expressions. I was very proud of that, and I found that exactly that had been derived by Morier 20 years before. But in principle, all that is laid down. There are a couple of there's one very important parameter which is really difficult to estimate, and that is cutoff. You know, in fluctuation dissipation theorem, you integrate over Q, and then you have to cut off your expansion somewhere. And it's discussed in our papers how to do that. That's not well defined. We are usually using just the average size of the Fermi surface as a cutoff. Yeah.
Yeah, one very short comment actually. You just mentioned discussing double exchange that it doesn't matter whether it's really Hudson couplet which wants to be ferromagnetic or this opposite sign which wants to keep an antiferromagnetic. It's indeed true that it's the same, the means is there. But if you take into account quantum effects, people have to be careful. If it's ferromagnetic, it's not necessarily spin up, but it's total spin triplet. It may be also up-down component of triplet. That's why actually it's not really completely forbidden to move on antiferromagnetic background, but it may be actually spin triplet component.
Okay, fair
It
enough.
actually was first mentioned by Eduard Nagaev, and that's changed actually this famous Degenfeld diagram. It's actually kinetic starts not directly as soon as you start doping, but there are minimum critical coupling. This might be important quantum effect, which maybe for you, for this calculation, is not important, but in principle, it might be relevant in some places.
Good.
You said that for quantum fluctuations, when one takes in the amount of local moment reduced by 0.1 to 0.3, something like this?
Oh, it can be it varies. It can be a lot. I mean, we know cases when it's like reduced from 1 to 0, like manganese silicon, for instance. Well, not to 0. That's to some. But there are examples when it's completely suppressed by fluctuation. We don't really fully. And these cases often sort of fall out of the standard Morier description, so we don't fully understand why sometimes these fluctuations are extremely strongly suppressing.
Okay, can you formulate very shortly why spin fluctuations should lead to the decrease of moment, not to increase?
Yes.
If I take
Yes.
palladium,
Yes, because it's more shallow on the left than on the right.
Yeah.
So, like, draw a line here, right?
Okay.
And take the
Okay.
center of this line. It will be to the
I
left.
reformulate the question. Palladium.
Palladium, yes. What about palladium? The statements, that's not.
Fluctuation should make situation even worse.
No. We did calculation for palladium. Yeah.
But then from right you have
No. In palladium,
the opposite situation.
No. In palladium, what you have in palladium is like this: that you have very, very shallow, near negligible minimum here, and then steep increase. That's what happens in palladium. So when you start, so in that case, your basically your even very small amplitude makes you non-magnetic because it fluctuates between left and right all the time. And if you calculate the derivative with respect to external field, then you get considerable reduction of spin susceptibility. In fact, you can get results in quite in agreement with experiments. We did calculations for palladium.
Due to fluctuation, you have
Yeah.
reduction.
Yeah.
After all, there is not a general rule of, in fact, what these spin fluctuations are going to do. You have to look at every system. However, you can say something which atom you are looking at, whether it's iron with respect to copper, with respect to manganese. So, for instance, copper, we know when you are coupled in a planar, so in a planar crystal structure, the magnetic moment is very robust. When you are in the iron pnictides, the magnetic moment there you have these effects which are much stronger. So
Well-
you can say some.
Yeah, I mean, definitely, this is what you are sort of looking at is a much bigger thing, is how much we can use chemistry, intuition in physics. And I think that you are right, we are, as a community, we don't use it enough.
Yeah.
We should use it more.
Yes, exactly.
Yeah.
Ask a very short question.
Sure.
Do I understand correctly that Liechtenstein's formula capture all the mechanisms you mentioned except for 90-degree exchange due to Hounsel oxygen, which requires self-consistency?
I never actually practically use Liechtenstein formula, so I may not be aware of intricacies of that. Igor would be in a much better position to respond. I think that on conceptual level, that 90-degree exchange should also be included, depending on how it's being implemented.
No, I don't think so. And also direct exchange.
It's also not there.
It's also not there.
It
Well,
requires the change of
let me put it this way. I think that force theorem, in principle, could be implied for both these cases. Maybe proper application of force theorem results in a different formulation than classical Liechtenstein formula. But again, I'm not really. I know what it is in general, but I never use it. I don't know the details of typical implementation.
But it depends how you do the force theorem around what ground state.
It doesn't matter. Doesn't matter.
No, it does. It does.
No. It matters, of course.
The question is how to treat the ligand state.
Results are equal.
Of course, you can treat them as a localized state. Then
No,
you can
let me put it this. Let me put it this way. This perturbation theory, well, let's call it a la Liechtenstein. If that theory includes explicitly the contribution of oxygen into the band structure, because the bands hybridization between oxygen and well, yeah. I mean, look, going back one step, force theorem is definitely applicable there, because you can if you do this canting properly, then the spin polarization on oxygen changes. And that has to be included on the level 4 theorem. What the formulation in terms of green functions that Liechtenstein formula implies, that may not be capturing that. I don't know. Probably, maybe it can be modified to capture that. But yeah. Anyway, I cannot say more.
So if there is no other questions, let's thank you.